Turkey, on the other hand, chump.
James, stop talking about turkey. This is math class.
We aren't doing that.
We are transitioning.
Oh.
Okay. So something that will be pretty forward for us, but it is new. We do need to spend just time talking about it. Is we've always, up until this point, only been finding the first derivative. We've actually talked about the second derivative a little bit, which I'll get to down here. But if you want the first derivative, you'll do what we've been doing. If you want the second derivative, you'll take the derivative of the first derivative. That will lead you to the second derivative. If you want the third derivative, you'll take the derivative of the derivative of the derivative. And it just stacks on the number of times you do it. It's not terrible. You're not going to ever have to do it more than 2 times, I don't think. But a couple properties that will come to light when we go over this. I just have here all the different notations, so there's just the prime notation. Once you get up to 4, they just start using the number 4. They're not going to do 4 apostrophes. Well, then, if you ever had to do the 55th derivative, you have, that wouldn't be so bad, but even Roman numerals get ugly, so they start using numbers. But here's where we've sort of touched on the second derivative concept. When we talked about applications and finding the derivative of the position function, you get the velocity. If you then take the derivative of velocity, what do you get? Acceleration. So velocity is the rate of change, aka the derivative, is the rate of change of the position. When you find the rate of change of velocity, you're talking about acceleration. And we only briefly talked about that, but remember that it goes position is your original function, the derivative of that gives you velocity, and then the derivative of your velocity gives you your acceleration. The examples on the bottom are just getting into second derivative. So we're given the original function. We first have to find the first derivative, so f prime of x. And Aaron, what's the derivative of x? 1, good. And Jane, what's the derivative of 32x to the negative second?
Negative 4x to the negative third.
Good. So there's our first derivative, just following some basic power rules. And then to get your second derivative, we're just going to take the derivative of that. So, Stefan, what's the derivative of 1? 0. So I don't need to write anything. And the derivative of negative 64x to the negative third.
196.
192.
No!
Now that we've finished, now we should clean it up. X to the negative fourth is just going to jump to the denominator and be x to the positive fourth.
Would you continuously write this?
Why are we doing this? Like, what is this going to branch into?
Just higher order derivatives. You just need to know how to find a second derivative because of this application more so than anything else. I think is the most practical application. By the end we'll talk about a couple connections with the number of times.
Really just going to say like,
Thank you.
like, is it just going to tell you the number of derivatives you have to find?
This is
Right.
easier.
And you said normally we don't go higher than 2.
You won't have to probably do it more than twice, but like again on the back they'll ask you to find the 10th derivative, but they'll give you the 8th. So then you just have to do the 8th to get to the 9th, and then the 9th to get to the 10th. But we'll get there.
Is there a different way to do this? Is this like the most complicated
No,
way?
there's no simpler way. Next example, what's our instinct? What would you do with this first? How would we find, what's the easiest way to find the first derivative? Okay, so I heard factor the top, although I don't think the top is factorable. James, what did you say?
I said split it into x squared over x and 2x minus 1 over x.
Right, I think the two options that are legitimate options are to actually do the division out and simplify this original function so that we've simplified it to x plus 2 minus 1 over x, and then take the derivative of that, because we've turned it sort of into a plain old polynomial. The other option would be the quotient rule, but I think that would be a little bit uglier. If you never changed it and you just started the quotient rule for something like this, I think it would just get a little bit ugly, especially when you then go to try to find the second derivative. So we're going to go this way, and I would rewrite this one more time to x to the negative first power. So it's got the polynomial structure. And then we can jump into the first derivative. The derivative of the x is 1. The derivative of 2 is 0. And the derivative of negative x to the negative first, we bring our negative out in front, so that's going to make it a positive x to the, and we're going to reduce this by a degree to negative 2. And then your second derivative is even easier because your derivative of 1 is gone, 0. And your derivative of x to the negative second is negative 2x to the negative third. And then just clean that up. And the last example I put down there is a trig one. Catherine? A 3. Any questions on that? Okay. First derivative of secant, what is it? Good.
Quickness.
We have to have those memorized.
Oh, that.
So those are that's the end of trig though. You have to have the sine and cosine ones, and then those 4. But that's the only trig stuff. So we've got sine, cosine. It's the 3 functions and all their reciprocals. Yes, you do need to know those. From this point, from the first derivative to the second derivative, what do we have to use?
The,
Product rule. Exactly. Secant x times tangent x. So your first times the derivative of tangent is I got it.
secant squared x.
Yeah, good. Great job, James.
Thank you.
First times derivative of the second plus the second times derivative of the first, the derivative of secant. Anthony?
Anything twice.
Oh, he got it the first time.
I don't even know what we're talking about anymore.
Okay.
Does it matter what word we use on it?
Oh, it's a multiplication, yeah.
Right, this was multiplication, so we talked about that. We're gonna do
Where
the,
are these coming from?
we're doing the product rule. So first times the derivative of the second plus the second times the derivative of the first. Are you saying you want to do the second times derivative of the first plus the first times derivative of the second? No, because it would just be the flipped order of addition.
Okay, that's.
Nope.
That's just another.
You're good. You're good. Now, from here, just to clean this up, we would make it, 1 second, Sonny, secant cubed plus secant x tan squared. And what again, from here on out, it's going to depend on what your multiple choice options are, what the back of the book says. So you want to make sure you understand how it can manipulate into different options. So that could be a final answer. I could see the potential for factoring out a secant x. And then you'd have secant squared x plus tangent squared x. When I see this, I don't know who's with me, but I immediately think of Pythagorean identities as being an option. I don't know if that's one, but I always go back to the one that I do know, sine squared plus cosine squared equals 1, and I try to play around with that until I get a tangent to come up. So the way I get there's two more other than this, I don't memorize them, I always manipulate this one into them. So if I want a tangent squared, I would divide everything by cosine squared, which will tell me one of the other identities, which is tangent squared x plus 1 equals secant squared x. So there is a relationship between secant squared and tangent squared. It's just when you add the two of them together, it's not like you get 1 or negative 1. But what I could, again, potentially see is I could see them taking out the secant squared and replacing it with tangent squared plus 1, which would just make it 2 tan squared, which would be a little bit cleaner looking in my opinion, but just know that Pythagorean identities might be utilized to clean things up.
You say that, isn't that you, aren't you the one making
I pull the multiple choice questions, I don't write them,
From what?
from old AP exams.
AP?
Oh.
This is AP Calc, so yes.
I don't know.
Didn't the AP exam just change it to
Mhm.
like 4 answers?
Mhm. Oh, is that how, I didn't know that was...
Yeah, I think that's how it is, and that they made the rubric harder, so to get like,
Oh,
5. Now it's like a 92.
okay. I knew it changed, I don't know the details of it.
Were there quizzes that we took before break? Are they
Mhm.
graded?
Not yet, no.
Alright, now it's
That was your question when I said, right, I'll get right with you, Sonny? Yes, Dominic?
Getting all of our test quizzes back, because I need to start.
Correction?
Yeah.
You're getting one back.
Alright, will
Today?
we get them all
Today.
back at some point this week?
Yes,
Will they go into the third quarter grade?
yes.
Alright.
Can we have a draw?
Yeah, we should drop one. That was
Wait,
it's Easter.
Moving on.
It's Easter present.
No.
Alright.
How's your availability?
Drop one.
Good, this week, good, not tomorrow, but... All right, so this is what I was talking about earlier. They ask us for the third derivative, but they're giving you the second. So all you have to do is just find your derivative of your second. Your derivative of 2 is? 0. So I don't need that. And then, I'm just rewriting the original, so this becomes x to the negative first, because that's going to make my derivative life easier. So when I take the derivative of the second piece, bring my negative 1 out in front, that's going to be a positive 2, x to the negative second, and then just clean that up. So you found your third derivative, but you didn't do the derivative 3 times to get there. Here's one asking us to go from the 4th derivative to the 6th derivative. So we just need to find the 5th.
What's the point of this? Like, what is this used for?
Well, the acceleration thing.
Yeah, but that's like 2. How far in does this go?
That's what I'm saying.
Like,
I don't get where this is going.
like what would the derivative of acceleration be?
I don't know. That's a good question for your physics teacher. I thought that same question myself this morning.
I bet Mike Hennessy knows.
Mr. Hennessy?
Big Mike?
Mr. Hennessy?
What is he like? Can you hear me?
He could if he wants to watch my calc video.
I don't think he does. I don't think he cares very much.
It's Mr. Hennessy to you.
Well, big stop.
Alright, so our 5th derivative, we have 2x plus 1, and what's the derivative of that, Kaylee? 2. And then from our 6th derivative, yes, Bailey, it is 0. 0.
So it's just 0 from the...
Yes. Okay. Here's an application problem with velocity. They give us our...
Do eventually they all get to 0 at some point?
Not negative exponents, because they'll keep going down and down. But we're given a velocity formula, and they're telling us the velocity is measured in feet per second. They're asking us to find the acceleration at different points in time. So if you're given the velocity formula, but you're asked for acceleration, we need to find the acceleration formula by finding the derivative. So v prime of t is going to give us our acceleration formula. And to find the derivative of this, I recommend the quotient rule. So bottom times the derivative of the top.
The exponent rule for the top and bottom and leave in the fraction? You see what I mean?
No, I don't see what you mean.
So 100t used to be 100, right?
No, we wouldn't have the quotient rule if it was that easy. That won't give you the right answer. Like 100 over 2, you want to say 50? No. So bottom times derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now, because they're asking me to evaluate this at 3 different spots, it probably will make my life a little bit more efficient if I clean up that top into distributing 200t plus 1500 minus 200t, and you can see why that helped. Your 200t minus 200t cancel. So your acceleration formula is 1500 over 2t plus 15 squared. And we need to find a of 5, a of 10, and a of 20. Your acceleration at the 5-second mark, at the 10-second mark, and at the 20-second mark. So with a calculator, because it's acceleration, I don't think a fraction is going to give us as much meaning as the actual value is going to be. So 1500, 2 times 5 is 10, 10 plus 15 is 25, so divided by 25 squared. I'll show that, but then I'm going to, on the calculator, get 2.4. And what's the unit on acceleration? Good. Feet per second squared.
Meters per second.
Well, this velocity was in feet, so this has to be in feet.
You gotta convert it,
So 1500, when I plug in a 10, I'm going to get 35 squared on the denominator.
If I write meters per second squared on a test, is that gonna get points off?
If it's feet, yes.
It's so lame,
Oh my
I'm
God.
so used to meters
Yeah,
per
it's
second
like-
squared.
I'm gonna write feet per second on my physics test.
1 point.
Tennessee would slap me. I see all the labels.
And then when we plug in 20, our denominator is going to be 55 squared. 1500 divided by 55 squared. So what's happening to our... Ooh, do that.
Decreasing.
Yeah. Over time, no, we're still accelerating. Our acceleration is still positive, but it's not accelerating as quickly. Okay? Which,
Reaching like a maximum speed.
right, you probably. It's more likely than not, I don't know, picture yourself
Terminal velocity, can I look up this?
going 30 miles per hour and then resuming back to a 60 mile per hour cruise control.
That is acceleration.
No.
Yeah, it is. If you're slowing down. Like if
No, you're going 30 miles per hour.
Okay.
You want to accelerate to 60
Oh,
miles
okay,
per hour,
I get what you're
but you do it via like hitting the resume button, and the car's going to like really rev early. So you're going to accelerate quickly, and then as you get to like 55 miles per hour, you're still accelerating, but it's evening
slowing the
out.
acceleration.
Exactly.
Can I
And
look-
that there would be the slope of the acceleration, the derivative of the acceleration. I don't know if there's a word for that.
Can I look up the derivative of the acceleration?
After class you can. Thanks for asking.
Everyone's wondering, Mrs. Rahal.
I really am.
Okay, couple true false here at the end. We have a function given to us, basic polynomial function in factored form, and it's saying that then the fifth derivative would be 0. Raise your hand if you have any thoughts on the truth of that statement. Noah says true. Why, Noah?
If the original function has a degree of 4, and every time you take a derivative, it goes down 1 degree.
Perfect, good. So, and actually, Sunny kind of commented on it that reminded me of this problem, but I'll talk about it when we get there. Your initial polynomial has a leading term of x to the 4th, which means if this is y equals x to the 4th plus a whole bunch more, the leading term of your first derivative is going to be 4x cubed plus a bunch more. And then the leading term of your second derivative would be 12x squared plus a bunch more. For your third derivative would be 24x plus some constant. And then your fourth derivative would just be 24. And your fifth derivative would be 0. So, yes, that is true. And then when Sunny said, and every derivative thereafter, your sixth, your seventh would also be 0. Okay? Number 2 has sort of the same idea, but we're given a function that's an nth degree polynomial, and this is saying that when we take the derivative that's 1 more than the degree, it will always be 0. What do you think about that?
True.
What's your counterexample if you think it's false?
What if you have a negative degree?
Good question. If you have a negative degree, so James's thoughtful counterexample is that what if you have x to the negative second? Then you'd be asked to take the negative 2 plus 1 would be the negative first derivative. Now there's some place we're not yet. We don't know how to take the negative. We only take the first derivative or the second derivative. We don't take the negative numberth derivative.
Can you?
Yes, we won't get there, sort of. We're not going to call it that, but yes, there's kind of a way to go backwards with it. The issue is, and so we don't really know enough to look at that yet, but I will also say this. Polynomials can't have negative exponents. Polynomials, by definition, it's a great thought for a counterexample, and it's exactly where your mind should go if you're trying to be creative and find a counterexample, but that's not a polynomial because it's a negative exponent, so this is true. And then if the velocity of an object is constant, then its acceleration is 0. True. If you're going 55 miles per hour and you're on cruise control, you're not accelerating or decelerating. So if you are going at a constant velocity, your acceleration is 0. I have your